morning, everyone. How's everybody doing? Questions while we wait for people to come in? Sure. Go ahead. It is a timed exam, absolutely. If you go to the exam schedule, there was a link posted. There was a link posted to the tentative exam schedule, but now that becomes the, it brings you to the real exam, and everything is spelled out in complete detail on the exam schedule. Again, go to the exam schedule. Everything is spelled out in complete detail over there. This will be our last class. Absolutely. Alessandro, we did that question in class already. We did that question in class, I want to say Thursday of last week. Jean-Christophe is asking about epsilon delta. Wasn't there something posted on, wasn't there something posted in the announcements or an email sent that there would be no epsilon delta proofs? Am I making that up? We are going to see newish material today. I mean, it's that was for continuity, yeah, but I mean, no, that's really the only place you would expect epsilon delta to come up. There's not going to be epsilon delta on the final exam. Could we do problem 8 from WebWork 8? I don't know what that is. If you can give it to me, we'll see. All right, so let me make it clear, no epsilon delta proofs on the final exam. Yeah. We will not do surface area for double integrals. I removed it. Well, yeah. So I mean, maybe you did it in the workshop, and that's fine. There were questions on the WebWork about it. I have removed them. We, time permitting, we would have discussed it, but that's it. I vaguely remember the work, play, sleep question. Let's not worry too much about it. What I want to bring your attention to, we did not do differentials, correct? We did not do differentials. Differentials come up naturally in a course on differential geometry. So if you want to, if you're interested in the study of differentials, that's where you'll encounter that. Instead, what I wanted to start off with today. We'll do a few examples coming back to cylindrical and spherical coordinates. But before we do, let's introduce that last topic. It's not really a new topic, but it's a generalization of what we were doing when we were doing transformations, cylindrical, spherical coordinate transformation. The point is that this generalizes to other kinds of transformations. The idea being that you just throw in the Jacobian. Let's take a few examples. Is the stuff from linear going to be included in the final? I don't think there's going to be necessarily a linear algebra question. Again, we haven't finished working on the final. I don't expect there to be a pure linear algebra question, but you know that everything you know about linear algebra plays a role here, right? So lines, planes, and all that stuff. Yeah, so what I want to do is other kinds of transformation, and let's just take an example, right? The point is, you know everything you need to know Jeremy, we can try that one a bit later on today. The final is a 3-hour final, right? So it's my understanding that you're given twice the time plus a half hour. So 6.5 hours. Please do not wait until the last minute to upload everything. We will not be accepting late submissions. So consider this. Let's draw a picture of what's happening. You have a vertex -1, 3. You have a vertex 1, -3. You have a vertex 1, 2, 3, 1. And you have a vertex 1, 5. That's unfortunate. Should have seen that coming. Right, there it is. And we'll draw it like this. Apparently, -3 is there. All right. Well, I mean, if they tell you it's a parallelogram, I mean, it's not really clear, right? I mean, we can work that out, of course. But there it is. And what's the point? I mean, you can do this easily, right? This is a double integral. You know what to do. And it turns out, right, that these vertices here are one on top of each other. So it's It's not that bad. And if you describe how y varies, well, y goes from here to there for a while until you hit that point, and then it goes from here to there. Describing how x varies would have been slightly more, right? X would have varied from here to there for a while until you hit that. And then it would have varied from here to there for a while until you hit that point. And then it would have varied from here to there. And you know, I mean, this parallelogram lines up very nicely, but if it hadn't, right, then describing x and y, you might have had to split it up into 3 pieces as well, right? Can we use symmetry here? It's a valid question. I don't think symmetry is going to help you, right? Because there doesn't seem to be symmetry about the x-axis or about the y-axis. So you cannot conclude that any of these two integrals is going to be 0. Yeah. So what am I saying? If you set it up dy dx or dx dy, you have to split it up into at least 2 integrals, possibly 3. And you know, I mean, it's doable. It's not the end of the world. But let's observe something. Here we're looking at the point 1 minus 3, and here we have the point, what is that? 1, 5. Oh, 1, 5 is not there at all. This is the 0.51. What happened there? This is completely wrong, right? Minus 1, 3. 1 minus 3. I didn't even draw 3 minus 1. Jeez, what happened? Minus 1, 3. 1 minus 3. 3 minus 1. And 1, 5. All right. Okay, better? Yeah. Okay, well, I mean, you know, still the same idea, because these are, right, one on top of each other. So if you describe dy dx, you have to split it up into 2 pieces. If you describe dx dy, then you have to split it up into 3 pieces. And if your parallelogram was just, if these had not lined up, you would have had to describe dy dx by breaking it up into 3 pieces as well. Let's look at the lines here joining these points. This has slope minus 1 plus 3, so that's 2. 2 over 2. This has slope 1. This is the line y equals x. And when x is 1, y is minus 3. So x minus 4, is that correct? When x is 3, y is minus 1. Very nice. This will have the same slope. Y equals x. When x is minus 1, y is 3. So that's going to be plus 4. Very nice. And here, change in y, which is 6. over -2, so -3. Minus 3x, and when x is -1, y is 3, so that does go through the origin. When x is 1, y is -3, and here y equals -3x. When x is 3, y is -1, so that is a +8. When x is 1, y is 5. Very nice. There it is. Right? Or y plus 3x equal to 0. Y plus 3x equal to 8. Y minus x equal to -4. And y minus x equal to 4. And you see that this screams out the following change of variables. Let u be y minus x. Let v be y plus 3x. This change of variables transforms this parallelogram in the xy plane to a nice rectangle in the UV plane, right? This becomes v equals 0. This becomes v equals 8. This becomes u equals -4. This becomes u equals 4. So u goes from -4 to 4. That is not u. U goes from -4 to 4. And v goes from 0 to 8. So I said rectangle, but you see that it's really a square. So this transformation transforms the parallelogram into a nice square. And so the integral just becomes an integral over a square. U goes from -4 to 4. V goes from 0 to 8. Well, now you have to figure out what x and y are, so you can work backwards. And you also need the Jacobian. Right? You're making a change of variables. All you need is to throw in the Jacobian. So if we, whatever you want to do, if we say v minus u, this minus that to get rid of the y's, you'll have a 4x. So x is v minus u over 4. And if you want to multiply this one by 3 and then add them to get rid of the x's, you'll have 4y is 3u plus v. So y is 3u plus v over 4. We need the Jacobian, which is dxy by duv. So dx du, dx dv, dy du. Well, maybe I should write that. Let's write it once. Dx du, dx dv, dy du, dy dv. So dx du minus a quarter, dx dv, 1/4, dy du, and dy dv. So that's 1/16 minus 3/16. So that's 2/16, 1/8. It's a minus 1/8. So is it minus? Wait, minus 1/16 minus 3. So that's minus 4/16 minus a quarter. Minus a quarter. You could. I was going to point that out. Thank you. Thank you. So first of all, we've calculated this. What people are pointing out is that if you calculate duv by dxy, right? Not the Jacobian we want, but duv by dxy. Thank you, Charles. Right? In other words, if you hadn't solved for x and y, because sometimes you can get away without solving. And if you just do duv by dxy, observe what happens. Du dx is minus 1. Du dy, dv dx, dv dy, which is minus 4. And you see how these two are rated, right? Let me write that down as a theorem. dxy by duv is equal to 1/duv by dxy. It's all true. So you don't need necessarily to solve for u and v in terms of, for x and y in terms of u and v. You could just do the Jacobian directly here and take 1/. Of course, sometimes that's going to be a function of x and y. Sometimes it's going to be a function of x and y. So you're going to want to rewrite that in terms of u and v anyways. How do we get u minus v? What would be minus u? Just subtract these. This minus this, the y's disappear. It's a nice linear algebra trick. Yeah, I don't have a proof for that. I don't have a proof. This is probably going to follow from the inverse function theorem. Yeah, I don't have any immediate proof for that. All right, so if we're making this transformation, x is v minus u over 4, y is 3u plus v over 4, Jacobian. Jacobian, or absolute value of the Jacobian, which is 1/4, du dv. So which Jacobian do you use? It's this one, right? That's why I wrote it as J. It's dxy by duv. All I'm saying is you could have calculated this one and done a 1/. That. All right. And the beauty here is that you don't have to split that up into 2 or even 3 integrals. One unique integral, you're good to go. If you wanted to go from polar to Cartesian, I mean, you'd have to work that out, right? Okay. So if you're going from xy to polar, are you missing a square root there? I think you might be missing a square root. Yeah, exactly. Yeah, exactly that. Somebody's asking, why is it 1/4 not negative 1/4? Right, you know that you throw in the absolute value of the Jacobian. Let's clean that up. The 4's cancel out. This is v minus u. 8 and the 4 cancel out to give us 6u plus 2v. The whole thing times 1/4. Let me take that out. du dv. Observe that u is odd, and you're integrating over -4 to 4. These both integrate to 0 by symmetry. So now nothing depends on u, so you just get 8. 8 times 1/4 is 2. And this is 3v, which is 3v squared from 0 to 8. 64 times 3, 192. How are we doing? As Niloy suggests, right? We decided on that change of variables from the graph itself. The function, the integrand, did not play a role in our change of variables, and we only came about after graphing the domain, noticing that the lines were the same, and so on and so on. The integral of u is 0 because u is odd, and you're integrating over -4 to 4. But again, you don't have to notice that. Go ahead and do the integral. I mean, it's going to be 5u, whose antiderivative is 5/2u squared. Nothing hard here. And everything works out nicely. You're going to get your 0 anyways. All I'm saying is if you notice symmetry, slightly quicker in this case. In other cases, it's a lot quicker, but so it's nice to. Can we try exchange of variables with triple integral? I actually don't have one. I don't have one. Could we split the original integral to 3 parts? Actually, you probably only need to split it into 2. So I'm going to invite you to do that. Redo the integral just in x and y. See which one is more work. Again, nobody is forcing you to make a change of variables here, right? Change of variables is only to help you. If you don't want to do it, that's fine. Jeremy will do that question right after. Thanks for rewriting it though. Why did the 1/4 come 2? Because when you integrate it with respect to u, there is no u now, right? Assuming these two go to 0. So we just have the 3v. So 3v times the length, which is 8. 8 times 4, well, 8 divided by 4 is 2. But again, don't take my word for it, just do the integration. You'll see. Let's take a moment to graph this. But, I mean, I think we see what's going to happen, right? Again, this is screaming out change of variables. But let's graph it nonetheless. Right here you have this first one here is x is y equals 1 over x. You know what that looks like. Y equals 1 over x. And the other one is y equals 2 over x, which is twice as large. I mean, probably an over-exaggeration there, but you see what's happening. And the other one here, this is y equals 1 over root x. So this is going, so when x is 1, right? 1 is really the tipping point. When x is bigger than 1, x is going to be bigger than root x. So the denominator is going to be bigger here. Your function is going to be small. Denominator is bigger, so function is smaller. So you'll have something like this. And then over here, it's the opposite. Terrible. So something like this. And what happens, and then it's going to intersect somewhere here. It's terrible, terrible, terrible. Just terrible. Let's say something like this. And then that one, which is just root 2 larger. Something like this. So there it is. This is the region we're integrating over. And again, you see the issue. If you're integrating with respect to y first, y is going to vary from here to there for a while until you hit this point. And then it varies from here to there for a while until you hit this point, and then it varies from here to there. So if you split it up dy dx, you have to, if you set it up dy dx, you have to split it up into 3 pieces. And similarly, if you want to describe how x varies, x is going to go from here to there for a while, until you hit that point, and then it goes from here to there for a while, until you hit that point, and then it goes from here to there. So a lot of work, a lot of work if you want to do that in terms of x and y. It's doable. I don't think the integrals are very difficult here. Everything is very doable. Well, you know, we like to be efficient. And you know, this is screaming out a change of variables. Right? If you let u be xy and v be xy squared, then it transforms this shape, this very weird shape in x and y, into what? Into u varying from 1 to 2 and v varying from 1 to 2 into this nice square in the UV plane. Absolutely, this is taken from page 1116. There it is. So if we're doing that, we should find the Jacobian. Again, you have options. How do we know when we have to change the variables? Or when do we know that we have to change variables? Well, that's the point. You don't have to. You don't have to, because you know you can do this in dy dx or dx dy. It's all good. Just a lot of work. I'm suggesting that you may use a change of variables here. And this is screaming out change of variables, right? xy, xy, xy squared, xy squared. So in the same way as with the parallelogram, which was really telling us to make the change of variables, so is this. So let's solve for x and y in terms of u and v and calculate the Jacobian. And then we'll also do it the other way, see the relationship between the two. Right? And again, a nice linear algebra trick. Observe that v over u is this divided by that divided by that. You see it. V over u is y. And if you square that and divide it by v, that is x squared y squared divided by xy squared, which is just x. Painless. Very nice. And now let's calculate dxy by duv, our Jacobian. Dx du, 2u, well, let me write it for completeness. Dx du, dx dv, dy du, dy dv. So dx du, 2u over v, dx dv, minus u squared over v squared. dy du minus v over u squared, and dy dv 1 over u. So what is that? AD minus BC, the u's cancel out, and you just have a v, 1 over v. So that is 1 over v. 1 over v. Let's, just for fun, Observe what would have happened if we hadn't solved. Right? What is duv by dxy? This is du dx, du dy, dv dx, dv dy. So this is 2xy squared minus xy squared, which is just xy squared. So you see, if you're making a change of variables, first of all, our usual way, right, and since we did solve for u and v, for x and y in terms of u and v, y squared is just v over u squared. Absolute value of your Jacobian, 1 over v, du dv, where u varies from, I think we had 1 to 2, 1 to 2. But if you're using this, if you're using that instead, what would have happened? You have your y squared. Jacobian would have been 1 over that. Right? The y squares cancel, but you still have 1 over x. So you still have to solve. And x being that, 1 over x would be v over u squared. So your integrand here would be v over u squared. Let's see if it's the same. This is v squared over v, so we get a 1v over u squared. Exactly the same. Exactly the same. How are we doing? Integrate with respect to u. We get 1 minus 1 half. So we get a 1 half v. Integrate with respect to v. 1/4 v squared from 1 to 2. 4 minus 1 is 3. 3 over 4. Yep, absolutely. Absolutely, very nice. Okay. All I'm suggesting is that sometimes it is actually worthwhile, because you know these questions are manufactured in such a way that everything works out nicely. Sometimes the Jacobian is exactly 1 over the integrand. I mean, the Jacobian this way, this duv by dxy, is actually the same as the integrand. So when you do 1 over, everything cancels, sometimes. Seldom, but I mean, it does happen. Well, you get, I mean, we didn't really use the graph to get the bounds, right? The graph were this equals 1, this equals 2, this equals 1, this equals 2. So you didn't actually need to graph to view the bounds here. And same with your parallelogram. We used the graph to get the equations of the straight lines, and then suggesting that this was really calling out for the appropriate substitution. And that's it. Right? Because here, I mean, yeah. How are we doing here? In some circumstances, you could skip the graph, and yeah. Yeah. Here, the only reason we did a graph was to convince ourselves that we did not want to integrate with respect to x and y. Yeah. And then made the appropriate substitution. So you see, you already knew all the important information about making this substitution, right? You need to throw in the Jacobian, and that's all. All right, let's do. There was a question suggested by Jeremy. Let's do Jeremy's question. Find the volume of the region that is below z equals a minus x squared minus y squared, above z equals square root of 4x squared plus 4y squared, and inside x squared plus y squared equal to 4. Thank you. Now, you know, when I said here that you don't need to make a change of variables, the takeaway is not that you shouldn't, or that you never need to, or that you can totally skip this part of the course. All I'm saying is, first of all, these change of variables are really only there to help you. They make your life simpler. So it's important to get a grasp of these. And a question on the final exam could very well force you to make a change of variables. Only to test whether you've mastered that material or not. Let's graph this, see and you know, moreover, I would make a very nice final exam question would be to do the integral two ways by making a change of variables and then just doing it in x and y and making sure that you get the same answer, which you can always do even if the question is not asking, right? All right, what do we have here? Let's start with this one. Do we want to start with that one? Whatever. You know what that is. We've graphed this many times, right? In the xz plane, this is a parabola coming down. In the, well, for some reason I've graphed it in the yz plane. In the xz plane, is that same parabola coming down, and you put everything together with circles, right? So you've got this bowl shape coming down. You have this which I'm sure you recognize, right? I mean, again, we've graphed this many times. If y is 0, z is plus or minus 2 absolute value of x. So you know what that's going to be. That's going to be a cone. And then we have this, which again, you know what that is. But before we graph that, perhaps we should ask the question, where do the cone and the paraboloid intersect? Do we want to answer that question? Suddenly I don't feel like answering that question. Oh, let's do it. Let's do it. If we look at this, this is the same as z squared is 4x squared plus 4y squared, or x squared plus y squared is z squared over 4. Yeah, exactly, right? We need to know. I mean, it did look painful, but here's the trick, right? Solve for z squared in terms of x squared and y squared and plug in that into here. So this, which is z equals 8 minus x squared plus y squared, that is just z squared over 4. So let's multiply by 4 to get rid of the denominator. And bring everything to one side. Z squared minus 4z minus 32 is equal to 0. Let me get rid of this Jacobian. And thus this factors nicely. Z minus 8, z plus 4. So this is when z is equal to 8 or z is equal to minus 4. But of course, since z is a positive square root, this never happens. So z has to be 8. So z has to be 8. And so these intersect. What has happened here? What's happening? Have I made a mistake? You found z equals 4. That's probably better. Somehow my positive 4 became a negative 4. Thank you. So this is plus 8 minus 4. Thank you. And so z is equal to negative 8 or positive 4. Right? I mean, the answer we were getting didn't make sense because if z was 8 here, then you had x squared plus y squared equal to 0, and it didn't match up with this one. So we knew something was wrong. Thank you, everyone. Thank you. So z equals negative 8 cannot happen because we're talking about the square root. So z has to be 4, and in this case, you get x squared plus y squared equals 4. And when z is 4 here, does that coincide? Squaring both sides, you get 16. And then you're going to divide by 4. You're good to go. Very good. Which is, so the intersection we get here is this disk of radius 2. So what is up? So we want below the paraboloid, above the cone, and inside this. What is up with that? Have we made another mistake there? Exactly, right? The cylinder is a redundant condition. It's all inside. Absolutely. Absolutely. What I was expecting when I originally read that question, I was expecting a smaller cylinder so that you would have had a cone like this, and then a part of the cylinder coming up, and then your paraboloid intersecting that cylinder somewhere here. That's what I was expecting, but that's not what happened. Right? This is completely redundant. Somehow there to throw you off. Or maybe give you a hint as to the fact that x squared plus y squared equals 4 plays a role. Maybe that's what they were trying to do. Yeah, as we suggest, maybe they were already telling you, but I mean, they didn't need to, right? I mean, you could solve for it with relative ease. Very well. So now that that's done, let's set up the volume as a triple integral, and you know that if you set it up as a triple integral, it's going to be the triple integral of 1. How does z vary? Well, clearly z goes from the cone to the paraboloid. So from the cone to the paraboloid. Jeremy has observed that it was actually minus. All right, very good. Well, so if it was plus, it would have been this. Let's do it with the minus. It's probably a better question. And, it's the same cone but pointing down. So we have this cone pointing down, and then you have this paraboloid. And then you have this cylinder. All right, that makes a lot more sense. That makes a lot more sense, right? Because at least now that cylinder is not redundant. All right. Very good. Everybody comfortable with what we're looking I mean, it's almost the same thing, right? It's almost exactly the same thing. How does z vary? Look at your region. Z is measured this way, right? This is the z-axis. Z goes from your bottom cone, negative square root, to the top paraboloid. Once z has been described, we project onto the xy plane, and you just get your disk of radius 2. Right, because you want everything exactly, nothing changed except the sign of the square root. So no harm done. No harm done. We just adapted our picture. And we're good to go. So the projection onto the xy plane is that great disk of radius 2, x squared plus y squared less than or equal to 4. Exactly right. I've left it like this because you see what's going to happen. We're going to switch to polar coordinates once we integrate it with respect to z. And for those of you, why not spherical? It's a good question. Why not spherical? Let's talk about why you probably want to, you probably want to stay away from spherical. Why? Your rho is measured from the origin moving out. So rho goes from here, right? I mean, now we want to describe our region here. Rho goes from 0 to the walls of the cylinder. But only for a while. Only until here. And then it goes from the origin to the paraboloid. So if you're using spherical coordinates, you're going to have to split it up into at least 2 regions. And as people have suggested, the paraboloid and the cylinder are probably not that nice in spherical coordinates. They're not terribly bad, right? The cylinder has equation x squared plus y squared equals 4. But x is rho cos theta sine phi, and y is rho sine theta sine phi. And if you square that and factor out a rho squared sine phi squared, you get cos squared plus sine squared. So this becomes rho squared sine squared phi. Or, if you prefer, rho is 2 over sine phi. So your cylinder has equation rho equals 2 over sine phi. Not terribly nice to work with, right? Especially as a bound. And so when you integrate with respect to rho, this is going to play a role. It's going to be some work. It's going to be some work. And that's just the cylinder. We haven't even talked about the top part, the paraboloid. And not to mention the fact that you have to split up your integral into 2 pieces. So seems like a lot more work than polar coordinates here. We actually don't need to find the intersection of the cylinder and the paraboloid because we want everything inside. So, you know, I mean, your cylinder is going to puncture both the cone and the paraboloid somewhere, and we're just restricting our attention to the inside. Marie had a question as to why it's less than or equal to and not bigger than or equal to. As Noloy suggested, we want it inside the cylinder. All right. I just wanted to point out one last thing, right? I mean, I know some of you may be still wondering why the integrand is 1 if we're looking for the volume. Right? Why the integrand is 1 when we're looking for a volume. Observe that once we integrate with respect to z, there is no z, right? So the integral is just z, plug in the top, subtract, plugging in the bottom. And now what do you have? Now you have the integral of the top function minus the integral of the bottom function. And that you understand to be the volume between the two. Marie's asking, why do we have 2 angles and not just 1? Are you talking about spherical coordinates here, Marie? Those angles were in the spherical coordinate suggestion that we're not going to do. Exactly. So we're not going to do that, right? And I mean, but it is important to understand why we have two different angles, right? Rho is measured from the origin moving out. Rho starts at 0 and goes all the way to the top, but only for a while until you hit this point, and then rho goes from the origin to the walls of the cylinder. So rho changes. That's the thing. So that's why we have to split it up into 2. But again, we're not doing that because it's too much work. Right? So if you were still unsure about the 1, convince yourselves top minus bottom. And that always happens. We're going to do the obvious. Switch to polar, because of course, integrating this with respect to x or with respect to y is a lot of work. It calls for a tangent substitution. Too much work. We're not that motivated. We're going to switch to polar. And what is this? Well, you know that this is a disc of radius 2. So how does r vary? Imagine having a rod of length 2 and spinning that around 360 degrees. You're going to touch every point in the circle. R goes from 0 to 2. Theta goes from 0 to 2 pi. In polar coordinates, x squared plus y squared, you have experience with that. You know x squared plus y squared is r squared. So this is 8 minus r squared, minus minus. If you factor out a 4 here, you get x squared plus y squared, which is again r squared. Jacobian, dr d theta. No thetas anywhere to be found. Let's integrate with respect to theta first, by Fubini's theorem. And then what? This is 8r minus r cubed. And this is 2r times r, so 2r squared. Integrate. This is 4r squared minus 1 over 4r to the 4 plus 2/3 r cubed from the 0 to 2. 16 minus 4 is 12. So 12 times 3, 36, plus 16, 46, 52, 104. 104 pi over 3. Anybody have that? I'm sure you finished that up a long time ago. Thank you. How are we doing? Questions? Do we have time for one more? Any requests? Anybody? Why don't we try this? Since the top paraboloid goes inside the cylinder, doesn't taking polar ignore that? No, because, right, these bounds already take care of the cylinder and, the cone and the paraboloid. So everything is described there. Yeah. Exactly. All right, let's consider this. This will be our last example. We'll end with that. Let's draw a picture of what's happening here. X squared plus y squared equals 1. You know that to be a cylinder of radius 1. X squared plus y squared equals 16. You know that to be a cylinder of radius 4. So we're looking at the stuff in between these two, above the xy plane, and then you're cutting it with some plane, z equals y plus 4, when so let's graph this in the YZ plane. When Y is 0, Z is 4. And when Z is 0, Y is -4, which, wouldn't you know it, just goes through this point. Right, so you have this line in the YZ plane, and then you're dragging that line in the X direction. So you see what's happening, right? You're going to cut your two cylinders slanted, and we're looking at the region. Yeah, there it is. Let's set it up, dz dy dx. How does z vary? Well, we want above the xy plane. So, right, z is going to start here and go up until you hit that slanted plane. So from 0 to y plus 4. And then, once we've described z, we project onto the xy plane, and what do we get? We get this shape between the two circles. So inside the large circle, but outside the smaller one. This annulus, if you will. And let's be smart here. Can we be smart? You realize that for every point x, y, z, in your solid, you have a corresponding point on the other side, negative x, y, z. Right? Does everybody see that? So if you think of doing a Riemann sum argument by having this box around that point, and same on the other side, where am I going with this? What's my conclusion? Anybody? Does anybody see what I'm suggesting? You know the deal. Somebody tell us. Anyone? No? The x integrates to 0. Very nice. The x integrates to 0. Again, it's nice to observe that, but if you don't see it, carry the x around, you'll see that that x part, the integral, will go to 0. Alexandra is asking, does it not also apply to y? But here's the problem, right? You see that this plane is on an incline in the y direction. So if you take a point x, y, z here, there isn't a point on the other side, x negative y, z, right? X negative y, z would be right here, and that's not in your solid. So it does work for the x, but it does not work for the y. Excellent. Integrate with respect to z. There is no z, so very easy. it would apply if there wasn't the cut exactly, or if it was horizontal, right? If it had a nice flat top instead of, yeah. All right, so integration with respect to z is trivial. And we get minus y times y plus 4 dy dx, where you are in that annulus between the two circles. You know what we're going to do, I'm sure. No, again, Nikki, you're not going to lose any marks, but it's just going to make everything longer. Now, and you know, again, not a big deal for us, I don't think. It makes your life a lot simpler. That's for sure. But no harm done in these easy questions. Like I said, though, in 264, the idea of symmetry takes all of its importance there. Marie doesn't understand why symmetry makes the x go to 0. Well, I like to make a Riemann sum argument. And here it is, right? I mean, because this triple integral here, we did a Riemann sum argument to understand that it represented a hypervolume, right? So what I'm suggesting is, look at your function. Let's just look at the x part, right? Because it's only the x part that goes to 0. So define a function w, which is x, and do a Riemann sum argument, right? So take a point, x, y, z, draw a small box around it of sides delta x, delta y, delta z. I've inverted the two, but you understand what that means, right? So take a small box around the point. This has volume, delta x, delta y, delta z. And now we're going to multiply by the height of your function. And at the point x, y, z, the height is just x. So you get a hypervolume, x, delta x, delta y, delta z. But your shape is such that on the other side, you have the same point x, y, z, but where the x is negative. So if you have that same box, if we do a Riemann sum argument again, you have a box of volume delta x, delta y, delta z, and now the height of your function is going to be negative x. Right, so you have a hypervolume here, a four-dimensional volume, negative x, delta y, delta z. Here, you have this volume, hypervolume, positive x, delta y, delta z. When you add them together, they cancel out. That's why the x goes to 0. If the integrand was x squared, we could not do that. Because x squared at this point is the same as x squared at that point. So then you could actually use symmetry and just do half and multiply by 2. All right, let's finish that up. You know what to do. We're going to switch to polar. Again, only because it makes everything so much easier. If you left it in terms of x, y, z, right? How does y vary? Y goes from the bottom half of the disk to the top half of the big one until you hit here. And then it goes from the bottom half of the large to the bottom half of the small until you hit here. And then bottom half of the large, bottom half to the top half of the large, and you're still missing this piece. In other words, you have to split it up into 4 integrals. Nobody wants to do that. Nobody. Not to mention the fact that the integrals would have square roots in them, and I mean, it's just going to be bad. Y doesn't go to 0 because of the top plane, exactly. You don't have that symmetry argument, right? If you took a point x, y, z here near the top, the corresponding point x negative y, z is not in your solid. Don't we have to check if the plane intersects the back of the bigger disk? It doesn't, right? Because, I mean, you see what happens. You have this large cylinder and you're cutting in right here. So this is the farthest point. So everything curls back in and your plane is straight. So you're fine. We're switching to polar. So y is r sine. R sine plus 4. Jacobian. R d theta. Where r varies from 1 to 4. Theta from 0 to 2 pi. Let's finish that up. Let's multiply everything. We have a minus r cubed sine squared minus 4r squared sine theta. Sorry. So antiderivative minus 1 over 4 r to the 4 minus 4 over 3 r cubed, and r is going from 1 to 4. So that is minus 64 sine squared minus, I want to say 256 plus 1/4 sine squared plus 4/3. Is that correct? Have I made a mistake? Anyone? Probably, maybe. I'll let you verify. It's 256 minus 1, 255. And this is 252. This integral is easy. You know how to integrate sine squared, right? Half angle identity. So that's minus 255 over 8. Sine squared is 1/2. 1 minus cosine 2 theta. Integrate. Theta minus 1/2 sine 2 theta. Minus 252 over 3 plus cos between 0 and 2 pi. Blah, blah, blah. This is 0, that is 0, and we're left with minus 255 pi over 4. Or is it the double angle? I mean, I always get them mixed up. I like to think of it as the double angle because it doubles the angle, but really the original one is half of the other one. I mean, the name is not that important as long as we know how to use it. Jeremy's asking how is the volume negative, but it wasn't a volume question, right? The original question was x minus y. So we had this four-dimensional function hovering above, and we had concluded that the x variable integrated to 0. So we were expecting a negative answer. Well, I mean, I'm jumping the gun here. I mean, we were, right? Because there is negative region for y, but the positive region is much larger. So we were expecting a negative answer. All right. How are we doing here? Questions? Yeah. Yeah, I mean, look, doesn't matter what we call it, as long as we know the identity and we know how to use it in this context, it's all good. How are we doing? Questions? Anybody? Maybe a good place to end then. Thank you all for coming. I will be available. I'll post extended office hours if you need to see me. Otherwise, good luck on your exams. How do I recommend you study? First, I recommend doing lots of exercises from the book. If you've done essentially all of them already, then you can move on to past finals to see how you would have done had you taken that course in those past years. But first and foremost, exercise from the book. So thank you, everyone. Good luck on your exams, and happy holidays if I don't see you again. You guys have a good one. And thank you all for coming.